My goal for this video is that it cover quite a bit of ground and not too much time. I'm going to work through 4 examples. We're still dealing with limits here, and all of the limits we look at today are going to be limits in an indeterminate form, and we'll see some more of the possibilities that can come up in that situation. So let's get started here. The first example is going to be the limit as x approaches 4 of x squared minus 3x minus 4 divided by x squared minus 2x minus 8. And what I want us to think about first is what will happen if I plug 0 in. So I know that these quadratic expressions on the top and the bottom are factorable, but I haven't really thought about that too much yet. But if I put in if I put in 4, I get 16 minus 12 minus 4 on the top is 0. And on the bottom I get 16 minus 8 is 0. So this is going to be in a determinate form. Another thing that I should remember from algebra is that if a polynomial function has a 0 for some specific value, or some specific value is a 0 of that function, then x minus k, right, where k is that value that made it 0, is a factor of the function. In other words, if putting 4 into the top makes the top 0, then x minus 4 is a factor of the top. And if putting 4 into the denominator makes it 0, then x minus 4 is a factor of the denominator. Since I know if I can make those factors show up on the top and the bottom, they can be canceled, that gives me the impression that I should be able to find a way to use algebra to manipulate this limit until I can determine what its value is. So let's go ahead and get started. I'm going to say that this is equal to the limit as x approaches 4 of the factored numerator, x minus 4 times x plus 1, over the factored denominator, x minus 4 times x plus 2, and then I'm going to cancel factors. Then this is equal to the limit where x is approaching 4 of x plus 1 over x plus 2, which is 4 plus 1 over 4 plus 2, which is 5/6. So once we get an idea of where we're going, an example like that works out pretty quickly. And just so that you don't start to get the impression that every time we have an indeterminate form, we must actually have a limit if we can just rearrange things correctly. Let's look at this next example. We're going to say the limit as x approaches negative 3 of x squared plus 8x plus 15 divided by x squared plus 6x plus 9. And factoring the top and the bottom lets me say that this is the same as the limit as x approaches negative 3 of x plus 5 times x plus 3 over x plus 3 squared, or x plus 3 times x plus 3. And then I can cancel x plus 3 on the top and x plus 3 on the bottom and continue on trying to evaluate my limit. I have now the limit as x approaches negative 3 of x plus 5 over x plus 3, which is equal to negative 3 plus 5 over negative 3 plus 3, which is equal to 2 over 0. Now I no longer have an indeterminate form. I have something that's undefined when I try to plug in the value where I'm evaluating this limit. So this limit is, even though it started in an indeterminate form, it actually does not exist. And that's why when we start with an indeterminate form, we say that maybe the limit will exist. It's not always true that it will. Let's look at a couple more examples where it will, where we have a slightly different method we need to employ to find the limit. So here's another example. The limit as x approaches 16 of the square root of x minus 4 over x minus 16. It's easy for me to see in this example that if I plug 16 in for x, I get 4 minus 4 is 0 on the top, and 16 minus 16 is 0 on the bottom. So what I'm going to do here is set this equal to the limit as x approaches 16. The top is going to stay the same, the square root of x minus 4, and the bottom I'm going to want to factor. Even though normally we would say x minus 16 is not factorable, right? It's a non-factorable linear denominator. But it turns out that I can factor it if I treat it like a difference of squares. So I'm going to say that x is really the square root of x squared. And then I'm going to use the difference of squares factoring technique to write this as the square root of x plus 4 times the square root of x minus 4. And not everybody likes this method, but it does work fairly simply and quickly. We now can cancel the square root of x minus 4 from the top and the bottom, and we're left with the limit as x approaches 16 of 1 over the square root of x plus 4, which is 1 over the square root of 16 plus 4, which is 1 over 8. Right, so that one worked out pretty quickly too. Last one we're going to look at is a situation where factoring is not really feasible in this case. So we've got the limit as x approaches 0 of x over the square root of x plus 9 minus 3. Putting 0 in for x gives us 0 on the top, and root 9 minus 3, which is 0 on the bottom also. And what we're going to do here is a method called rationalizing. And we're not going to, in this case, we're going to rationalize the denominator, but that won't always be the case. We could end up rationalizing the numerator in a different problem. So in order to rationalize this irrational denominator here, we need to multiply by its conjugate. So we're going to multiply the bottom by the square root of x plus 9 plus 3. And we're going to do the same on the top, the square root of x plus 9 plus 3. So essentially we've multiplied by 1 inside this limit. And we're going to rewrite now as the limit as x approaches 0. And on top, we're not going to do any distributing. And we'll see why in a second. Really, it's because we're looking for ways to cancel. So we're just going to leave this as x times the square root of x plus 9 plus 3. And on the bottom, we are going to distribute. So square root of x plus 9 times the square root of x plus 9 is x plus 9. We know the whole point of multiplying by a conjugate, sorry for that pop-up, is that square root of x plus 9 times 3 and the square root of x plus 9 times negative 3 cancel. So the last thing we have is negative 3 times 3 is negative 9. So looking here, we've got 9 minus 9, those go away. Then we just have an x left on the bottom, which we can cancel with the x factor in the numerator. So we can write a new limit. This is equal to the limit as x approaches 0 of the square root of x plus 9 plus 3. Now, we don't even have a denominator anymore, so there's nothing really to keep us from plugging 0 in to this function. So we get the square root of 0 plus 9 plus 3 is equal to 6. So there were 4 quick examples of ways that we can evaluate limits in indeterminate form. Hopefully they're helpful. If you missed any as I rushed through those, feel free to go back and re-watch certain parts of the video, pause where you need to. That's what these videos are for. So have a good day.